Okay, so continuing on with gas laws, we're going to introduce the concept of the mole fraction, and that's kind of a takeoff from Dalton's law yesterday, and then we're going to move on to the ideal gas law. So I need you to have out your calculators and be ready. Mole fraction is a really easy idea, and again, it goes hand in hand with Dalton's law. So let's say in this room, we talked about yesterday the total pressure of the air outside, or our atmosphere, let's just pretend in this room, is equal to the partial pressure of all the individual gases, right? So let's just say there's these three gases in the atmosphere around us, O2, N2, and CO2. I know there's more, but just for the sake of argument. In addition to figuring out what we call partial pressures, we could figure out something called mole fraction. Mole fraction is exactly what it sounds like. It's the fraction of moles in a system. So let's say I had 0.7 moles of O2, and I had 0.3 moles of N2, and I had 1 mole of CO2. What fraction of the moles is CO2? Half. How'd you figure that out? Part over whole. That's exactly what you did. So here you put part over whole. Now notice when I asked, Grant, for instance, yelled out half. I asked for mole fraction. Did anybody yell out 50%? No. Okay, you yelled out a fraction. So a fraction is what we're looking for. A lot of students try to convert these to percents. They're not supposed to be percents. They're supposed to be a fraction. But here's the kicker. Saying 1/2 is actually not good either. Anyone want to guess why in this class saying 1/2 is not good? Not that 1/2 of what. I'm okay with the half part. What did you say, Alex? Sig figs. Why is 1/2 bad? Is that a number with sig figs? No, that's basically kind of like a counting number. It has an infinite number of sig figs. So when you report your fractions, they have to be in decimal form. So instead of saying 1/2, you'd say 0.5 or 0.500 or 0.5000, whatever. You just don't use the fraction half, and you also don't convert it to a percent. I was part of a question many years back, actually, that had mole fractions on there, and if you multiplied it and made it a percent, they wouldn't give you credit at all. But what's really cool about the mole fraction is you can use the mole fraction to find a partial pressure. So if you know the total pressure of this system, for instance, and you know that it's half CO2, or you know its mole fraction, you can figure out the partial pressure of the CO2. So if this were 600 millimeters of mercury, for instance, and we know the mole fraction of CO2 is, what, 0.5, what would the pressure then, the partial pressure of CO2 alone be in the system? 300. And that's what's really cool about mole fractions. So we're going to specifically use them to just figure out partial pressures of gases and systems. It really couldn't get any easier. So it says the mole fraction is indicated with an X, of nitrogen in air is 0.7808. Calculate the partial pressure of nitrogen. That's what we're looking for. If the total pressure, they say atmospheric pressure, whenever they say that, that is the total pressure, is equal to 760 torr. So how would I set that up? Exactly. 760 times 0.7808 is equal to, come on, calculators. There's 20 of you with calculators right in front of you. Come on. 590 what? 593 torr is equal to the partial pressure of the N2. Okay? It's that simple. The partial pressure of oxygen was observed to be 156 torr. With an atmospheric pressure, what is that? P total of 743 torr. Now they want us to find the mole fraction. How do I set that up? P total times what? Mole fraction of O2 is equal to the partial pressure of the O2. So 743 times X is equal to 156. So what is our mole fraction of O2? 210. And you leave it like that. Don't say 21%, and don't try to make it 1/2 or 1 whatever that is. I don't even know what that would be. 1/5-ish. Okay. We're good with mole fractions. That's all about mole fractions you need to know. Simple. All right, we're going to move on to the ideal gas law now. Pervnert. I say pervnert. I know physics says pivnert. A lot of people say pivnert, but I like pervnert better because it sounds like pervert, and that's just more entertaining than pivnert. You really need to watch units when you're doing this. All the units are based on this universal gas constant. This universal gas constant can be given to you with different units. We can also take it from the gas world to the thermal world and make it a totally different number. Does 8.31 sound familiar to y'all? Joules per mole K. That's just a conversion of the same kind of number. They're all the same, but they have appropriate units for whatever we're looking at. This gas constant units, I kind of want you to commit to memory. I know it sounds crazy, but I have a little way to remember it. Latam molk. Latam over molk. Latam molk. I just don't know why it sticks in my head. If you know latam molk, you'll always know what units your items have to be in order to put them into the ideal gas law. Using this R. There is an R for the pressure of millimeters of mercury. There is an R for the pressure of torr. Those would be the same. It's like 68.4 or something. But on that AP equation sheet you have, the insert on the exam, this is the R that you have. And so, well, they actually might have the other one. But anyway, just always use this R. The less confusion is going to be a product of less R's. It's good. So let's look at this problem. What is the pressure required to confine 0.460 moles of an ideal gas at 33 degrees Celsius in a volume of 9.50 liters? Think back to yesterday's problems we did where we were doing all that dimensional analysis and we were using the combined gas law and all that. How is this very different from yesterday? Well, we did moles yesterday in Avogadro's law. We had more than one variable in the combined gas law. It's already equal to some close. Peter? Exactly. This set of conditions is one set of conditions. Everything we did yesterday, we were trying to find something out as conditions changed. Y'all see the difference? Okay? So this is just one set of conditions that are not changing. So all we do is take the numbers and plug them in. I do expect you to do the good old unsubstituted equation, substituted equation. And then as far as unit conversions, I'm going to show you a trick, which I'll accept if you're consistent with it. You can plug stuff in. So we have 9.50 liters here. I do want you to, for the sake of not making errors, write down those units. It's going to help you. And our moles, 0.460 moles. Our R is 0.0821, and I am out of room. I should have moved this over. Latam molk. Our T, this is where the trick is. We have to add. You need to show conversions on the AP. So rather than doing it on the side and plugging it in, go ahead and just do it this way, if you want, within the equation, and then you've shown it, and it's plugged in, so all you have to do now is put it in your calculator. All right, so what do we get for our pressure, and what would the unit be? 1.22, and the unit? Atmospheres. Okay? So the best way to show your conversions is actually in the problem itself. So if you had, for instance, a pressure and you needed it to be in atmospheres and they gave it to you in millimeters of mercury, within your equation you could do divided by 760 in the actual equation and show your conversion that way, and they take it. Yeah? Yep, that is the universal gas constant, 0.0821, and it always goes into R, and you have to know those units. Now, you might have learned it in pre-AP where they did a dimensional analysis where you put stuff in and cancel things out with just the units of R. You can do that if you want, if you like it. I just like plugging and chugging into Pervner. Elsa. I use atmospheres because this tells me everything that has to be the units in the equation. Otherwise, it wouldn't cancel out. Okay? Atmospheres will cancel out with those atmospheres. Yes? No, it's not it's just a unit. It's not this is not a formula. Okay? If I ask you what the units on density are, what would you tell me? Grams per mil, right? So these are just units. When you try to determine density, do you plug stuff into grams per mil? No, you plug it into mass over volume. So these are just units on a number. Okay, let's move on to a practice problem. Now, you might know the answer to this before we do it, but we're still going to do it. Determine the volume of 1 mole of gas at STP. We're going to use ideal gas law. We're going to determine at STP. So what pressure is correct at STP? 1 atmosphere. We're looking for the volume of 1 mole of a gas. This is the unit, 0.0821. You put your units down, lat/molc, times the temperature of no, not 298. 273 is the standard temperature in gas laws. So this is what I want to show you with these units. The K's cancel here. The atmospheres will cancel here. These moles cancel. So what will your volume come out to be in? Liters. Go ahead and solve. What do you get? 22.4. Where have you heard that? One mole of any gas at STP has a volume of 22.4 liters. Up to this point, you've just memorized it, but this is why, right here. This is also known as molar volume. Okay? Only at STP is that 22.4 legit. It's going to change, and you see now why. If temperature or pressure changes, doesn't that number change? Yeah? Because of PV equals nRT. Okay, so is everybody good with the ideal gas law? You're going to need to practice on your homework. But now I'm going to introduce a new character above, and this character is going to help us find one of two things. If we need the density of a gas or the molar mass or molar weight, same thing, of a gas, there's a special formula I'm going to introduce you to. I'm going to show you how to do it with the formula, and the only drawback to using this formula is it would be something you'd have to memorize. If you don't want to memorize a formula, I'm going to show you another way. But the formula is actually really easy because I have a way to remember it. So if you look up, you see that little cat in the box? That's the molecular weight kitty cat. The reason I call him the molecular weight cat is because he makes a noise. What do all cats say? Meow. Do you see how that's meow? And this is only for gases. So think of cats being stinky and gas, okay? Now, when a cat goes in the litter box and they go to the bathroom, what do? What? They bury it, right? Have y'all seen that? Okay? So what cats do in the litter box is they put their dirt over their pee. Say what? Oh, it still smells, unless you have what I have, which is the phenomenal automatic litter box, which also has the crystals that absorb, so you never have to scoop it. It's amazing. Go science. All right. What we're going to do here is utilize this equation to find either molar mass or density. And it's phenomenal because I'm going to show you the other way to do it, and you're going to be like, yeah, this is better. All right, so using the information, we need to find the density of oxygen gas at STP, the density. One thing I need you to pay attention to are the units on density. I'll show you how they come out. But we don't do grams per mil in the world of gases. We do grams per liter. Does anyone want to guess why? Why would I need a liter to weigh instead of a mil? Because what? There's more substance. I'm not going to have a very good balance that's going to be able to measure out the mass of something as small as a 1 mil of a gas. It's so light. So we're going to use larger sample sizes. So density of gases, we look at grams per liter, and you'll see how the units turn out that way when we do this. So what is the molar mass or molar weight of oxygen gas? Not 16. It's diatomic. We're solving for density. R is our same gas constant, 0.0821 latam molx. Temperature says STP, so it's 273. Pressure, STP, 1 atm. So let's look at the units for a second. My atmospheres are going to go. When I divide by moles, that's going to go. What else goes? Kelvin goes. What does that leave me? Grams and liters. That's why my density is going to be in grams per liter. So go ahead and just solve that density. Just, cross multiply. 32 times 1 divided by 0.0821 divided by 273. And what do we get? Units? Grams per liter. So that's the molecular weight kitty cat for molecular weight or density. I'm going to show you how you can do this an alternative way down here. And you guys get to decide. I'm not going to judge which way you do it. It's going to be 100% up to you which route you take. So if you're solving for density, you're going to need what two things? Grams and liters. Okay? The only thing they told us in this problem was we have oxygen gas at STP, which means they told us STP, they told us 273 Kelvin at 1 atmosphere. So that's all we have. And we need to find the density of this. The only thing I can do in a problem like this is play the pretend game. There's a couple ways to approach it since we're at STP. I'm going to approach it the way that you would do if you weren't at STP, the way you can do it all the time. I'm going to pretend I have 1 liter of a substance. Because if I pretend I have 1 liter, that's what I'm going to put here for liters. I can pretend I have as much as anything. I can pretend 50 liters or whatever. So if I pretend I have 1 liter, what's all I need then to figure out density? Grams. Usually grams come from what? Moles. In the world of gases, where can I get moles? What equation? Easier. Okay, we're going to hold on. Hold on to the 22.4 thing. That's only at STP. I'm solving this problem for any temperature and pressure. If I want moles at a temperature and pressure, what equation do I use? PervNert. So what I'm going to do is take PervNert, and I'm going to plug in everything, pretending I have a liter, and get moles. So I know I'm at 1 pressure, ATM. I just said I'm pretending 1 liter. I'm going to solve for moles. This is 0.0821, and my temperature is 273. So how many moles is that? Someone tell me the moles with a calculator. I don't need Rain Man making attempts in the back row. 0.0446? Is that right? All right, so those are moles. I know moles in a liter now, but what do I need for density? Grams. So for every 1 mole I have 32 grams. Let me erase that. For every 1 mole, Molar mass, 32 grams. So what do I get for grams? Oh, 1.43, looky there. That's how many grams are in 1 liter, because I pretended a liter. Now I'm going to address that 22.4 in a second, but does everyone see what I did? I pretended I had a liter, I used PervNERT to solve for how many moles that is, and then converted that to grams. So which way do you like better? Dirt over P? Yeah, so I do. Now, because we're at STP, what we could have done is, it's still just as long, we could have went ahead and said, hey, I have a volume of 22.4. If I had a volume, let me just extend this even a little further. If I had a volume of 22.4, knowing I need density, if I have a volume of 22.4, I know how many moles that is. How many moles is that? 1 mole. How many grams in a mole of oxygen? Right? And then I can solve for it that way. But that's only at STP. And I wanted to give you a way that you can solve using any conditions. Any pressure and temperature here, this method will work. Unless you just want to use dirt over P, which I think is a good idea. All right, I'm going to do the next one. Are you okay if we do just dirt over P on this one? All right. A compound has an empirical formula of CHCl. A 256 ml flask at 373, so I've got 256 mils at 373 K and 750 torr contain 0.80 grams of the gaseous compound. Give the molecular formula. If I have the empirical formula and I need the molecular formula, what one piece of information do I need? Molar mass, and that's what I'm going to solve for. So the molecular weight kitty cat is perfect. The molecular weight kitty cat puts his dirt over his P. So now I can just plug and solve for molecular weight. Molecular weight is equal to, density is grams per liter, so it's what? What do I write? 0.8. Good, I'm glad you all caught that. Over 0.256 liters. My R is my universal gas constant. My temperature is 373 K. And then my pressure is, divided by 760. Why? I need atmospheres here. Torr won't cancel out. So this gives me ATM. So what I would do if I were you, I'd write in the equation, you could do this, write ATM next to it like that, so you can show the grader you know you had to do that conversion. All right, so solve for my molecular weight. What? 96.97 grams per mole. That sounds about right to me. So if I know the molecular weight, that's not the question. The question wants to know the formula. So what will I have to do to figure out the molecular formula? Perfect. Figure out the weight of the empirical formula. And then what do I get? Oh, this board. It's not working now. Awesome. Right in the middle of the video. It's frozen. Yay, the board's frozen. So I guess I'll talk you through this. Oh, I think it's back. 48 point, so that's the empirical formula mass. How much larger is the molar mass? It's double, right? So what does that make our molecular formula? And there it is. You're going to learn probably about 5 different ways in this class just to determine a molecular empirical formulas. So you're using a totally different method to find a molecular formula other than doing what you've done before. Okay? Y'all good with this one? Yeah? Okay, and what does the molecular weight kitty cat do? Puts what? Dirt over P. Okay. And there she is. And then on her collar, you can see a little, the collar says MW. It's molecular weight kitty cat. All right. Last problem. This is easy. It's just taking stoichiometry to another level. It's using stoichiometry to either get into or out of PV equals nRT. So when I do stoichiometry and I always draw that arrow, what did I call that? That arrow? The mole bridge. So to be on the mole bridge, you had to be in moles. So you can use PV equals nRT to get moles, to get on the mole bridge, or to take moles off of the mole bridge and convert it to something else. So in this problem, hydrogen can be prepared by passing steam through a hollow air tube, blah, blah, blah. Calculate the volume of H2 formed, and they're giving us a set of conditions, when, this is atmospheres, when 98.3 grams of water are passed through the tube. We're assuming this is an excess. So any ideas of how I'm going to do this? I know I have to, this is my known, I got to get to here. What can I find from that mole bridge? Now, not ratio. We're going to convert to moles. I'll give you that. But I got to get volume. If I know moles, how do I get volume from moles, atmosphere, and temperature? Pervnert. Okay? So let's go ahead and do stoichiometry to find moles of this guy. 98.3 grams of water. How do I mole bridge? For every, got to get to moles first. For every 1 mole of water, I have 18.02 grams of water. So my grams of water cancels. Now I'm in moles. Now I can mole bridge. For every 4 moles of H2, I have 4 moles of water. Do I need to go on? No, I'm going to stop it here, and I'm going to find moles of H2, which would be what? 5.46 moles. That's a lot of moles. All right. So now I have moles of H2. What do I do next? Plug it into Pervnert to find volume. So my pressure they gave me was 0.98 atm. The volume they gave me, they didn't. I'm looking for it. I have 5.46 moles. My R is 0.0821 lattimolc. And my temperature, 723 Kelvin. So what you could do in here is write 450 plus 273. I'm okay with that. If you don't, you need to show the conversion somewhere else. 330? Wow. 300, and let's look at our sig figs. 1, 2, 3, 1, 2, 3. That's 1, 2, but we'll make it 3. Oh, let's just do 330 because there's 2 sig figs there as well. So 330 liters. That's a lot of liters. Is everyone good with stoic? So this is really the only problem I'm going to do. You can practice this in homework. It's literally the exact same thing you've already done, but then taking that information and using Pervnert. They might do it reverse and say how many grams of hydrogen are produced when they give you 5 liters of a 0.7 atmosphere, blah, blah, blah. So you'd have to find moles to get here first and then mole bridge over to whatever you're looking for. So they can mix it up and do it anyway. What I want to talk about real quick, which is really important, is tomorrow's lab. We're doing it online because it's incredibly difficult to get good results. But rather than you just doing it at home, I'm taking class time to do it because it's really, really important you learn the procedure. Does everyone understand what I mean? Okay, so the new AP is heavy on lab procedures. So what I'm going to do right now is just talk you through the procedure. You're going to do all of it again tomorrow in the actual lab, but I want you to understand how it's working. It's a really simplistic procedure, but the whole point of tomorrow's lab is to find the molar mass of a volatile liquid. We're going to meet in the Shrieking Shack tomorrow in the library. So be sure to go there. I'll have a note on the door in case you forget. Bring your lab books because you have a pre-lab due tomorrow. But and you'll have time today during the activity period to pretty much knock it out. The molar mass of a volatile liquid is a really common method. What does volatile mean? Not unstable. Smelly. Okay, I'll take smelly, but why is it smelly? Not reacting. It evaporates very, very easily at pretty low temperatures. It goes from liquid to gas readily. Okay, so even though we seem to be doing something with a liquid, it's actually us manipulating a gas to figure out the molar mass of this stuff. So what you do is you start with an Erlenmeyer flask. I just want to draw pretties. That's so hard. All right, so there's my Erlenmeyer. Okay? The first thing you're going to do is you're going to weigh the Erlenmeyer, and you're going to get a grams of your empty flask. Okay? And then I'm going to give you a volatile liquid, like an alcohol or an alkane, like pentane or something, and I'm going to say, tell me the molar mass of this. I'm not going to tell you what it is. You're going to follow the instructions, and the first step is to just dump some in here. Doesn't really matter how much. You're going to dump, I think the instructions might say either 2 mils or 5 mils. I can't remember. Okay? You're going to dump some liquid in there. And then you're actually going to put a little cap on it, and you're going to get the initial weight of the flask and the little aluminum cap as well together before you dump the liquid in there. Then you're going to dump the liquid in there. Then you're going to take your little flask, and I can't remember in the online lab if they have you use a Bunsen burner or if you're putting it on a hot plate. Is it a hot plate? Okay, so you must be someone that did that lab accidentally. Okay. I've done this in the lab many times. I've used every different method possible. I used Erlenmeyer flasks. I used test tubes. The results are so crazy bad that you guys would be so focused on your 6,000% error, you would miss the point of what we're doing. So that's why I've chosen to make it an online issue. And using the Bunsen burner, I've had fires because the liquids are so volatile that you get a lot of gas formation around the area, and so that easily catches on fire, and it's been an interesting few years trying to work through this lab. But what you're going to do is take your sample with your little bit of liquid in there, and you're going to heat it up. What's going to happen as you heat it up? It's going to evaporate. So you're going to get this liquid evaporating, right? There are a few holes in your little cap, so you're going to see waves of gas coming out. How many of y'all have seen, like in the summertime, if it's hot after it rains, you can kind of see the waves coming off of the pavement? You know what I'm talking about? That's how it looks. That's exactly what it looks like. And you're going to do this and heat it right when the waves stop. And when the waves stop, you're going to take it off. What has happened when you're heating it? These molecules of gas have spread out to fill the flask perfectly. Any excess gas that can't fit leaves. So the second you see it stop, you pull it off, you are assuming that this volume is full of gas. And by this volume, I mean the volume of the flask is totally full of gas. So then you're going to take it, and you'll either, do they have you put it in an ice bath on the online or just put it on the counter? You put it on the counter, and it cools. So what happens to this gas when you put it on the counter again? It recondenses, and so you're back to having liquid. Once the glass is cool and everything's cool, you're going to get the weight again of the flask with your cap on, but this time it's going to have liquid in it. And so by subtracting, you'll know your grams of your sample. So we know grams of sample. The lab instructs you to, at the point you remove it, at the very point you remove it, you're going to read the barometer and get the pressure. You're also, this is in a water bath, I believe, and there's a thermometer. You're also at the point of removal going to read the temperature. So you've got pressure, you've got temperature, you've got grams. How about the volume of the flask? My Erlenmeyer is not meant to do good measurements. It's only actually got graduations to here. We got all of this extra. How do you think I'm going to find the volume of that flask? Any ideas? Don't say anything. No, I don't know it. I don't know. I can't count. I got to figure it out. I need that volume to do my calculations. Geometry. Okay, so you're going to take a ruler and you're going to measure it. Close, but no. Let's think of another way. Think. Displacement. Close. So what are you going to do? It's a good idea. Okay, he's saying to fill up a tank of water and see how much you displace. That's close. There we go. You're going to fill the flask with water and then pour that water into a graduated cylinder, right? Won't that tell you the volume? Okay, so you're going to then figure out the volume of that flask that way. All right, so what's the moral of the story here? I have got pressure from the barometer, temperature from the thermometer, volume because I figured out the volume, grams because I did the subtraction and weighed it. How is that going to help me find molar mass of that liquid? How do we find molar mass? Kitty. Dirt over P. Grams divided by liters. R is a constant. We have temperature and pressure. Solve for the molar mass. It's a pretty sexy little method, and it's really simple if you think about it, but it's pretty powerful that you can come up with the molar mass of something based on that. So I found some people got great results. Other people for pentane would get a molar mass of 8,000. All right, that's it. Announcements. Pre-lab due tomorrow.